Hello everyone. Welcome to Amazon ML Summer School. And today we will be uh, talking on the lecture on reinforcement learning. I am Sayambu, and I am an applied scientist in Alexa in Amazon. And I'll be covering part one, the introduction to reinforcement learning. Let's begin. What is reinforcement learning? In your previous lectures, you might have seen supervised learning and unsupervised learning. In each of those topics, the learning was somehow either the data was not given to you and you use some other implicit features of the data to learn, or the labels were given to you and you learned using some objective functions. Reinforcement learning is done through interaction with the environment. There is no right answers. You only get reward signals on interacting with the environment and getting to some state which is desired. And it is mostly a trial and error search with a delayed reward. And the goal is to maximize the cumulative reward over time. The reward hypothesis, as given by Sutton and Bartu, all goals can be described by the maximization of expected cumulative reward. Let's see what we mean by that. The three ML paradigms are supervised, unsupervised, and reinforcement learning. In supervised, the input output pairs are given and you learn the mapping between them. In unsupervised, there is no label data, so you discover the hidden structure within the data. And in reinforcement learning, you are not given the label directly. You have to interact with the environment to get to the reward at the end of your interaction. And the main difference is no supervisor, only reward. Feedback is delayed. In supervised, the input directly gets the output. In reinforcement learning, you take a set of actions and at the end, you know whether you got the reward or not. And time matters in reinforcement learning. And the agent's actions affects the future data. The intuitive is that analogy is that supervised learning is the student with an answer key and the correct label is given. The model learns to predict the output given unseen input or seen input. In unsupervised learning, you use the data itself to learn clusters, and it may have some mapping or may not have any mapping, but it learns to somehow figure out the inherent structure within the data. And reinforcement learning is about agent or a model putting an action to the environment and getting rewards. And there is a lot of trial and error interaction, and you get scalar rewards, often delayed. And the examples, of course, is that there's image classification in supervised learning. In unsupervised learning, it is clustering, dimensionality reduction. Reinforcement learning is about game playing, robotics, and ChatGPT. Let's get to the RL framework now. So this is the agent environment and action loop. Given the current state, the agent takes an action and then the environment, given the action from the agent, and of course the current state of the environment gives you the next state and the reward. The agent learns about the current state and then learns what is the long-term goal that can be learned given the reward from that. So at each time steps, agent observes state, selects an action based on some policy pi, and then the environment transitions to a new state along with giving a reward, and then it is repeated. Let us see this. So, as you can see, the agent is giving an action to the environment. There is some dynamics within the environment where the probability of the next state, given the current state and the action, is there. And then the next state is sampled from this dynamics. This probability may or may not be known, but if you can see, it is very simple that you start somewhere at t equal to 0 And then suppose at time t equal to 1, you take some action, say move forward, and then you reach the then you reach a fork. Still no reward. You still exploring. And then you can go one of either ways. You chose the correct way, and then you reached a reward. And then you get a treasure, of which is a reward 10. So start, hallway, and fork are the right actions were taken, but you don't know the reward of them until you reach the final state. And you get a cumulative reward, which is uh, from each time step, starting from time step t equal to 0, you get the reward equal to the reward of this plus, as you can see, it's sum of gamma to the power of k of r of t plus k plus 1. So it's this reward plus gamma into this reward plus gamma square into this reward plus gamma cube into this reward. That is what it is finally giving us 7.29. Let's see again. The key components is that the agent is a learner or decision maker. It's, you can say something similar to classification, but the classification is about the correct classes, and here it's about the right actions. And there can be different type of actions. As you can see here, it can be a discrete action or a continuous action. Even within discrete action, you can have deterministic policies, or you can have stochastic policies. So deterministic means that given a state, you have exactly one action. Stochastic policy means given a state, you have a probability distribution of the other action. So 60% probability of going to the left, 30% of going to the right, and then you sample at the time of going to the right distribution. Why stochastic? Because exploring or trying new things gives us new states. And given those states, we then learn to move to more favorable or bad or worse, less favorable states. And we won't know that until we reach the terminal state. The policy pi, which is a rule for choosing actions, and as I said, it can be deterministic or stochastic, but it can be learned. How it can be learned, what does the policy look like, we'll see later on. So let's talk about episodic versus continuous tasks. What does this mean? So as I have shown earlier, that there can be for each action, it moves to the next state. That next state can be uh, that next state can be very it can be fixed along certain paths. For example, an episodic task means that given a start state, you can take some steps to move to the next steps, and then you reach an end. So that is an episodic task. Continuous task means there is different states, but you can move among those different states altogether. For example, in this particular part, there is a fixed episodic state. So it moves to the start, goes to the hallway, fork, and then treasure. But there can be states where you are moving between the same states again and again. And that is what is known as a continuous task. There is no terminal state. Till S3, you can move to S0, or there can be infinite number of steps. There is no natural endpoint, and it needs gamma less than 1 for finite return. Otherwise, if gamma is equal to 1, which means all rewards are important, what would happen is the cumulative reward can get infinite. And in that case, the time horizon on which we are calculating can go very high. And the examples, of course, in episodic task is like chess, maze, card pool, while continuous task is stock trading or server control. Because in stock trading, there is no end state, right? You're continuously checking the stock, and based on that, you're making some action. It will continue forever, as like till the end of humanity. And that can be called as like infinite states. Similarly, server control for motors. A motor does not reach a state and then stop. A motor will continue moving forward or backward, a server motor. And so that is why it will be a continuous task. And the important thing is in episodic, the return can have gamma equal to 1. You can have gamma less than 1 also to control the horizon, but important part is there is a fixed number of steps. So you are always calculating the total return among that fixed horizon. In continuous tasks, it is important that it can go up to infinity. So that is why the reward needs to have gamma multiplication over the horizon. And unified, all we have to do is t equal to infinity or gamma equal to 1, but not both. And this is an example of a code of how a reinforcement learning method works. You initiate an environment using OpenAI's Gym is one example. And then for each step, you take an action based on the observation of the state. And then you take an action based on that environment. uh, and then the environment gives you observation reward, the information whether it's terminated at that state or not, or it's truncated or not, and other metadata info. If it's terminated or truncated, we just reset the environment and start from scratch. And it's a fixed number of steps for training or moving through the policy, but 1,000 over here. But either way, there is a terminated state. So let's talk about some real world applications of reinforcement learning. So before that, let's do a little MCQ. What do you think best distinguishes RL from supervised learning? I'll give you some time. So it is that RL learns delayed reward signals because there is no teacher providing the correct actions at each step. It only receives a scalar reward that may be delayed. So what are the applications of reinforcement learning? Uh, in 2017, DeepMind developed a reinforcement learning agent that learned to defeat the world champion at Go. And that model was trained using reinforcement learning. And then that agent was trained partially using human data and partially using reinforcement learning. But they developed AlphaGo after that, 100 to 0, which did not even require any human games for it to learn. It just simulated all the different states and learned the best strategy to defeat the world champion. In 2013 to 15 was when we first saw reinforcement learning's great uh, abilities, where it learned to play the Atari games, which were the 2D games in the 90s. And it was able to play a lot of them just via raw pixels. We did not have to create any representations for those games or anything. It just gave was given the raw pixels, and the actions were the game actions, which was in this case up, down, left, right, space bar, or any other controls. And it learned to play those games so well, it was actually able to beat humans at a lot of these games. And finally, in 2019, OpenAI created a agent which was able to play 3D games, Dota, and then it was actually able to defeat pro players just by using self-play. It did not need demonstrations from any type of human players. So, what does that mean? What is common among all of them? The common thing among all of them is that what we have in our case is a simulation environment which can actually let the model play among itself millions of times to learn from its mistakes. And, and that is what is happening over here. In all of these cases, The video game, Go game, and Dota 2 game, these are available to everyone. And what needs to do is simply plug a model to observe these and take actions among all the possible actions. And using some clever learning tricks for reinforcement learning, you can actually learn a lot from the failures and the few wins that are there without using human data, and it will eventually learn to do the best among all of this using simple models that uh, is learned using reinforcement learning, and it's not very different from what we are about to learn today. And the applications across domains is that it is being used in industry and in technology. The most significant application in today's world is that a lot of the large language models like ChatGPT, Claude that you see use extensive reinforcement learning to intelligently extend the domain of the models beyond what is given by human data. Industry, it is actually a very common use of reinforcement learning to use for representations and also for learning to move among robotics. So this is one application where you simulate using a simulator for robot data, and then you use it along with the real robot to learn common representations. And using this, you can actually train a robot in simulation without having to actually turn on the robot. And then you just deploy it to reality after that using those similar mapping between the simulation and the target domain. And of course, there is other applications like self-driving uses a lot of reinforcement learning. Finance and portfolio optimization has a lot of applications in reinforcement learning as well. The milestones is mainly gaming is where reinforcement learning initially showed promise, and right now it is used for large scale reasoning models, and it is what allows DeepSeek like models to do so well across a large number of use cases without having seen a lot of data in its training. Let's now begin with the Markov decision process, which is at the fundamental level of reinforcement learning. So, a Markov decision process can be defined by this five tuple: the S, which is the set of all possible states, the A, which is the set of all possible actions, and the transition probability function, which says uh, what's the probability of moving to the next state given the current state and action. There is rewards that moving from state to S to state S dash, taking action A, what's the rewards? And then there is the gamma. How much will you discount the rewards in the future? And using this five states, once you define them, all reinforcement learning models uh, problems can be reduced to the same equations that in different formulations. The Markov property is important here, and it states that the future is independent of the past given the present. And the current state contains all the information needed to predict the future. We do not need to remember history. And this is an important property of where reinforcement learning works well. It is not that we don't need all the past information, but assuming this makes modeling simpler. And that is the objective that we will try to show here, that making the modeling of reinforcement learning simpler, we don't need to worry about what the long states were. As long as the current state contains sufficient information to encode the past, We just need to focus on the next action given the current state and the approximated long-term reward from that state. And some example is that chessboard position. We don't really need to know how it got to a chessboard position. Given the chessboard position, we know uh, all the different future plays that are possible. How long have I been driving? That is not Markov alone, because you do need to know what was the start time many hours ago or whatever time ago to know how long you have been driving. And transition probabilities are how we model the system to show that given a current state, we know everything about how to move to the next state in order to get to the right goal. And this is a grid world example where the state can be assumed to be the coordinate. So in this case, it is 1, 1 coordinate. And in this, we can model the probability of the next action uh, as different states. And the property of the transition probabilities is that it should always be greater than equal to 0 for all S dash S and A. And the sum of all probable next states given the current state and action should be 1 for all states and actions. Uh, there is more to it in this formula, but for now, we are just keeping this for simplification. And as you can see in the grid world over here, that the probability over here of moving right is higher than the probability of moving to the top or uh, bottom. And since the probability should be 1, there is no probability of moving to the left, as you can see. And it encodes the environment dynamics in a way, but what the model is trying to do is learn the uh, environment dynamics. It does not know the transition probabilities, and for most of our problems the transition probabilities will not be known. Let's talk about the reward functions and the discount factors. Reward function is a function of the state and the action, and it's a scalar signal at each step, but usually it is 0 until it reaches the terminal state or some desired state, and it defines the goal. In a cart pole type of problem, it is like +1 per step, pole stays up, and -1 per step for speed. And at the correct goal, it is +10 and -10 at trap. Discount factor is how far are you willing to see the discounted rewards, which, as I mentioned earlier, it is the sum of the rewards till the sum end state. So it can, if it is summation of gamma to the r to the power of gamma, uh, sorry, it's gamma summation of gamma to the power of k into r, where k is from 0 to whatever is the terminal time step. In episodic, it will be some time step t, and in continuous, it would be infinity. Gamma equal to 1 means no discounting, which means the 10th step reward is the same as the current step reward. So it can be risky because in that case, the cumulative reward can get too high for us. So, and that might diverge our functions. So that's why it is always better to have some sort of discount so that there is convergence of the infinite sums, and it also takes care of uncertainty about future. If, say, during your current run, your ending is somewhere at a bad state where you get a negative reward, in that case, discounting those far steps is better, so that the current state, which might lead to a good reward, is not removed. And we do have some myopicness where cash now is better than cash later. Let's see the interactive demo of what this means. So as you can see, for gamma equal to zero point 0.9, so gamma to the power of k into r, as time step increases, that gamma to the power of k reduces, and hence the uh, effective return keeps on getting lesser and lesser. And the effective time horizon uh, based returns keeps on getting higher as it's increased. So what does that mean? That means that if in path A, suppose you get a reward plus 5 now and then plus 1 per step, then having a gamma equal to low will also be okay, because as you can see, the immediate reward gets good. And the effective planning horizon is like quite high in that case, because we are only seeing the current reward. But as the gamma gets high, this same weight will have, this current reward will have the same weight as the very far reward. And the future remains important in that case. If there is a delayed reward, as you can see, then gamma equal to 1 is high and the effective return is good. But if gamma is low, then that far away reward, as you can see, is going to be a problem and it is not taken into account. So path B will not be chosen most probably, because early on it will learn that if I take the plus 5 step now, that is better for me. So yeah, gamma equal to 0 means agent only sees immediate reward. Gamma equal to 1 means agent values all these future rewards equally. Gamma point 0.9 is the typical choice. Far-sighted, but still convergent. And you can tell why not gamma equal to 1 for infinite horizon, because summation of 1 to the power of k, where gamma equal to 1, very close to 1 would mean 1 by 1 minus 0. It's a divergence sum. So with gamma equal to zero point 0.9, what is the effective planning horizon of the agent? And what happens if gamma equal to 1 in a continuing infinite task? I'll give you some time. So it's B. The effective horizon is 1 by 1 minus gamma, which is equal to 10 steps. And gamma equal to 1, the infinite horizon means that it will be summation of R, which is 1, which is infinity. And hence it will diverge. The cumulative discounted reward. So in the previous steps, we did not assume anything about the next step. We just kept waiting until it reached the terminal state and then did the discounted rewards till that end. And the total discounted reward from time t forward can be seen as rt plus 1 plus gamma into gt plus 1. And this is important because this is an approximation which we will later take. And this is what effective horizon means. That if we go further, then effective planning horizon uh, keeps on increasing. Uh, as you can see, this is effective horizon 100 steps. And for gamma equal to 0, effective horizon is 1 step. And an example of this is the grid world or the card pool. Let me show you what it looks like. So in this, the left diagram is the grid world's state values. State is the coordinate for each of them. And in this is the policy, what it says of where to go, right? And we are choosing a gamma of zero point 0.9. Let me show you what happens. So we just let it run until it reached some terminal state. And in this, we found that uh, all the states for gamma equal to zero point 0.9, which means uh, more or less high value. But Only at it was mostly just randomly roaming around at these cases, so most of them have -1. But only after coming here, it learned that going here is good. So that's why you can see that it learned that effective value at this state is good because somewhere we can reach high. Over here, it learned that the value is bad because going above means -10, and it's a terminal state also. This is also a terminal state, but this is a terminal state which is going to end badly. Let's learn another iteration. So as you can see, the value at each consecutive closer to the step increases somewhat because it is learning that from this step you can get to a better state. Over here, look at what is happening. Going up is the best. The Q value is increasing. Going down is bad. And going to the right is absolutely bad. And hence, that's why a good upper state and a bad rights action is what is contributing the V to go low. But it knows that somewhere there is a good terminal state. And as you can see, these are all bad. And as I keep on doing this, you can see that it is slowly learning which are the good states to reach. So the point is the are going to reflect that way. That if you reach a good state, that means you're close to the good terminal state. If you reach a bad state, it is better to not go towards those states because it is going to uh, cause poorer actions in those cases. And you can continuously do this. And this is according to the greedy policy, where given the best Q value, which is the state actions value together, uh, you can get to a very good state. So you can see what happens till we converge. So at convergence, these states close to the terminal state are bad. This has somewhat higher value because from here we can get to the good terminal state, but we can also get to the bad terminal state. So you can see the value of this state and action up is good, but the value of this state and action going to the right is bad. So that's where the averages are going quite poorly. But going down is not bad again because the value over here is good. And this is something known as value iteration, where we find the reward of the state and action plus the gamma into summation over all the next states uh, given the current state and action and the value of the next state. So over here, if the next state is here, then you do the next state over here, and you can see there's a max action. So the value is, and this is called optimality, the value is taken over the action which is best. Then there is random policies. I'll reset it over here. So over here, if you continue, you can see that the policy is not learning anything according to the values. The policy is just taking random actions. So because it is taking random actions, the values also are not learning anything. Because from each state, it can take any random action. So all states get poor value. Let's see card pull. So you can see here the card pole over here, and the point is there is no balance over here. The terminal state in this case is theta greater than 12 degree or x, which is the cart position being greater than 2.4 or the time being greater than 5. And it's mod theta so and mod x. So that means either way 12 degree it would go bad. So suppose I move to the right. So if I move to the right, as you can see, the cart is moving, but it's also being pushed away. And then once it's reached the -12 degree, it's over. So let's reset. And then let's take an auto balance. And you can see that it is basically learning to take the right actions over here. We can do a little bit of pushing. So you can see as I'm moving to the right, the cart position is changing, velocity is changing, the pole angle is changing, and the pole angular velocity is also changing. This is the state, and it's of four variables in this case. In the grid world example, the state was the coordinate. In this case, it is the cart pole's position, velocity, and the angle and angular velocity. And at each time step, as we had defined earlier, reward is +1 as long as it is within this -12 to +10. And you can see that we are just calculating the total return. So we move to the right enough. Now let's move to the left a little bit to try and save it. But as you can see, it was almost falling, but I managed to save it. And because of this, you can see that the total return is increasing. And now this time it fell again. Let's talk about it. In a grid world with stochastic transitions, the P of going to the right given the current state and going to taking an action to the right is zero point 0.8. Up given the current state and right is zero point 0.1. Down given is zero point 0.1. What property must hold? It's C. It's that the transition probabilities must sum to 1. In this case, they do sum to 1 over all the actions. Let's now look at Bellman equations. So, Bellman equations tell us value functions of states or states and actions. So, let's start with the value function of a policy pi. So, state value function tells us what's the value of a current state S under the policy pi weighted by the average of the policy pi's probability over actions. And this tells us, uh, as you can see from the diagram, that starting from state A, what's the weighted average based on the pi, which tells us the probability of an action given the state S, and the sum of probability of all actions given the state S will be 1. So it is weighted average of the next state's reward plus gamma discounted average state of the next state. And as you can see, uh, it uses the policy pi to weight actions, and at the later stage, we weight using the next state transitions. An important point to note is that we don't always have access to the transition probability. So we will see later on that this transition probability can be approximated with just the value function. Uh, we'll discuss that later, but uh, the important part is this is just the reward plus gamma into the value that we or a cumulative return approximated by the value function. And it's a system of linear equations, if you can see. So from value of S, we will see an equation of all the different next states, and you can see it's all linear. So that's why it will be easy to solve as well, given we know the state transition probabilities. So this is an example with for two-state MDP where there are two states and we can either stay in the current state or go in the next state. And we can see here is that the V pi s uh, pi stay given S1 into 2 plus zero point 0.9 into V pi S1, which I said was uh, the removing the average over B pi S dashed with the sample and plus pi go given S1 into 0 plus zero point 0.9 because in this we are assuming the reward of staying at S1 is 2 and going from S1 is 0. Similarly, V pi S2 is pi stay given S2 into 1 plus zero point 0.9 because reward of staying in S2 is 1, and 3 plus 0.9 V pi S1, because uh, going from S2 is reward 3. And as you can see, it's a linear equation because the rest of it is just simply uh, equations that we don't need to solve for. The pi is assumed to be given. Solving this 2 cross 2 linear equation, we can get the uh, optimal value with the pi's. Let's now look at Bellman expectation. The Bellman expectation with Q says what is the value of state and action, and it will be immediate reward plus discounted average Q value of the next state. So unlike the previous one where we took an average over actions, here we are calculating each action's value. So states actions is given. For that, all the different states that are there, we take the next state rewards in that uh, next states. But Q value also requires actions. So that's why the Q value requires averaging over the next state's actions, not the current state's actions. So that's what it means. Q value of state S and action A is immediate reward plus discounted average of Q at next state and next action. And the key difference is that the root is the SA, not just S. And also it must also averaged over next A dashed. If you see previously, this one is averaged over S dashed, but not over A dashed because we don't need it. So V backup is S to A and S dashed. Q backup is SA to S dashed and A dashed. And VS evaluates being in a state. QSA evaluates taking an action from a state. And the relation between VS and QSA is that uh, if you do V pi S, if you notice, this is actually Q pi S of A. So V pi S will be sum over A of pi of A of S weighted by the action probabilities of Q and S and A. That is what is said over here. And we can get the value function of S from the Q value of S and A. And Bellman optimality equation is nothing but our older value function, which was given here. But instead of taking the weighted average over pi of A given S, we now just take the max over actions. So if Vs is sum over A pi A given S of Q of S and A, then V star of S, the optimal equation, would just be the max over Q of S and A over the current states, all possible actions. And the difference is that it's non-linear because it's not a linear equation anymore. You can see over here that V star of S and S1 is max of QS1 stay and QS1 go. Similarly, V star S2 is max of QS2 stay and QS2 go. It cannot be solved by linear equations, so we need to use iterative solutions to get to the right state. We'll see that over an example later on. Let's look at the Bellman Explorer. So you can see this is a optimality. This is a two-state MTP where there is state 1 and state 2, and V star gives you the optimal value functions. And as you can see that V star of S1 is max of 2 plus zero point 0.9 into V star S1 and 0 plus zero point 0.9 into V star S2. Similar for V star S2 as well. We can change the gamma over here, and what we will see is V star S1 chooses the max, and also we can say using argmax what's the best action. So despite the V star S1 being smaller than V star S2, it's still choosing the action of optimal policy to stay. That's because the optimal policy is chosen over the argmax of V star S1. So on staying, we find it is 2 plus 0.81 into V star S1, and in that, we find this is greater than 0 plus zero point 0.81 into V star S2. Similarly, uh, in S2, go is the optimal policy because the max is the next term. So We can try playing with this. So you can see the current reward S1 and stay is 2, S1 and going is 0. So let's try increasing the reward of going from S1. As you can see, the policy has changed now because this is the action for going and the reward is now high. So the optimal value into gamma plus the reward makes it better to go. So now the optimal policy is always go because the rewards are always higher in going for both. Let's try decreasing S2. As you can see, when you decrease S2 enough, there comes a point where actually staying in S1 is better because you can see staying in S1 is 2 reward. And because of that, the optimal policy at S2 becomes to go to S1 and the optimal policy in S1 becomes to stay at S1 to get the maximum cumulative reward. Important point to notice, these are not terminal states. So the Bellman equation can be found this way. And on changing the policy values, you can see that the value function changes. Gamma changes a lot more drastically, but it does not change the overall policy. So V pi S1 will be greater than V pi S2. And the policy will depend a lot more on the reward. And for Bellman optimality, you can see that optimal value will always be greater than the policy functions. So you can see that QS1 and go is changing, but QS2 and stay is decreasing. And the best policy becomes at S1 to stay and at S2 to go. So this is important to know for the difference between optimality and expectation is that optimal value will always be greater than the policy pi's value. We can change the gamma or change the policy pi, but they will only just try to match up with the optimal policy values. You cannot exceed the optimal policy values using a current policy. So that's what Bellman expectation says. How good is the policy? Optimality says what is the best policy? And you can check. The solution is matrix inversion and optimality is value iteration. So we'll see a worked example now where similar to the one in the simulation that you saw that at S1 uh, you have staying of reward 2 and going is reward 0 and at S2 staying is reward 1 and going is reward 3. So Bellman optimality improves a policy by looking one step ahead and calculating the total value of every possible action and forcing the agent to choose the absolute best option. So this is called policy improvement. How it works is we start with the current value, the V pi S of the current policy, and it tells you how good your current strategy is. And then we calculate the Q pi values of SA for each of the actions at each state. And then for each state, we now say that the new policy is choose the argmax of Q pi SA and it gives 100% probability to the best action. This is the new pi now. And using this, you can now calculate the V pi of S. And there is a theorem which says P I dashed using the greedy policy will always be greater than the current policy. This is a worked example I've been showing you. Assume that pi is stay given S1 is 1 and go given S2 is 1. It's deterministic. So we can solve the policy equations, the value function equations, and you can move it in a matrix form. Just doing simple matrix inversion gives us the value of the policy pi, and there is no iteration needed. Let's now go to the optimal policy and see. We now calculate the QPy values for each of the stay and go actions for each of the states, and then we just choose the policy to be the argmax. At the end, we find that the policy is the same, which means that we are now already at the optimal policy. And that's how policy iteration is used. You start with a some policy pi zero, evaluate it, and then improving using the optimality equation. And then again you evaluate it, and then again improving using the optimality equation. Remember, the while optimality from the current state gives you the best action, it's not the best state. And as I said, optimality is non-linear. So that's why it can improve if you calculate over all states and actions infinitely enough. And Bellman equations are the foundation of all RL algorithms. And you will see in your later modules that they are used for Q-learning, DQN, actor critic. DQN is actually the model which was used for the Atari games that you have seen earlier. And if you know about dynamic programming, you will see it's very similar principles. We solve a suboptimal problem of the next state and use that to try and solve the overall equation. And self-consistency means that value of the state must agree with successor values. And there is a contraction mapping theorem which says that as long as the discount factor gamma is less than 1, it is guaranteed to converge. Let's see if you can answer this question. What is the key difference between Bellman expectation and optimality? The answer is that expectation averages over actions weighted by pi, while optimality takes the max. So, in summary, today we have learned that reinforcement learning is interaction from the environment and learning via delayed rewards. The framework is that an agent interacts with the environment to get rewards. It looks at the state and gets actions. And using that, we calculate values using the Bellman equations. And the Bellman equations can be linearly solved or iteratively solved using recursive decomposition. And value function V of S and Q of S and A measure the goodness of the states and the states and actions. These are the books that you can use for further reading, Sutton and Barto. And there are amazing video lectures of David Silver and Stanford and Berkeley lectures you can get for much more in-depth learning. Thank you.